Here we go. So, when we were together last, we talked about step 7 of glycolysis. This is where we are able to recover a molecule of ATP. And maybe I'll just back up to remind you of where we've been. On Monday last week, we talked about the retroaldol reaction of fructose 1,6-bisphosphate that converts the 6-carbon carbohydrate into 2 3-carbon units that are interchangeable in a subsequent step. And one of these is an aldehyde. That's really important because aldehydes are highly reactive. They're at the top of our list of reactive carbonyl compounds. In the next step, dihydroxyacetone phosphate gets converted to glyceraldehyde through an enediol intermediate, same way that we converted glucose 6-phosphate into fructose 6-phosphate. And then we have this interesting step where an aldehyde gets converted to a mixed phosphoanhydride. Notice that the carbon that used to be an aldehyde is now at the carboxylic acid oxidation state. And notice, but that the free energy of this reaction is close to 0. The reaction's reversible, meaning the aldehyde is so reactive that you can go to a mixed phosphoanhydride and it not be a huge change in free energy. This involves an oxidation step, so it consumes NAD+ to generate NADH. And you end up with this 1,3-bisphosphoglycerate. You've got a phosphoester on carbon 3, but that's a more stable bond than the phosphoanhydride that is on carbon 1. Okay? And so when we left off last time, we were going to use this very reactive mixed phosphoanhydride to create a new phosphoanhydride in ATP. So basically this is a kinase style reaction. The enzyme that catalyzes this reaction is called phosphoglycerate kinase. And this is an interesting name because it's actually named for the reverse reaction. Remember, kinases transfer gamma phosphate groups. In the forward direction, though, ADP picks up the gamma phosphate from 1,3-bisphosphoglycerate. In the reverse direction, you'd start with this product, 3-phosphoglycerate, and then phosphoglycerate kinase would transfer a gamma phosphate from ATP to the carboxylate group. You will see this all over in biochemistry. It will irritate you, but you got to sort of suck it up and deal with it. Enzymes are sometimes named for the reverse reaction. Mechanism is what you would expect for kinase reactions. Here, the terminal negatively charged oxygen from the beta phosphate group of ADP acts as a nucleophile attacking the gamma phosphate in 1,3-bisphosphoglycerate. You generate a pentavalent intermediate, which then collapses to kick off the leaving group. This is a little bit more in detail. The kinase reactions that I've shown you is in a little bit more detail than your text shows. Your text simply shows an SN2 type reaction, though there is evidence for a pentavalent phosphorus intermediate, which is why I've drawn the mechanism as we have so far. Okay. And then just to make things totally clear, I'm going to draw the structure of ATP so that we can demonstrate the new bond that we made versus the old bond that we broke, and so that you can see how both before and after the reaction we've got intermediates with similar stability. So I'm running out of space for the ribose ring of ADP. We'll just write A there for the base. Okay, and notice over on the left-hand side, this bond here is the mixed phosphoanhydride bond, and the new bond that we made with by converting ADP into ATP is this bond between the gamma and the beta phosphate groups. And it's essentially similar in stability, which is why this reaction is reversible. And we pointed out last time that this is a payoff step. We're generating, for every molecule of glucose, we have 2 molecules of glyceraldehyde 3-phosphate. So we just paid off our ATP debt. Now, once we get to 3-phosphoglycerate, we're pretty close to the end of glycolysis. But if we want to generate another equivalent of ATP, we got a problem. And our problem is essentially that the remaining phosphate group in 3-phosphoglycerate is not attached to a good leaving group. In fact, this bond is a fairly stable phosphoester. So you would not expect ADP to be able to come along and attack this phosphate group, because the thing that would leave would just be a negatively charged alcohol, terrible leaving group. So for the remaining 3 steps of glycolysis, it's all going to be about getting the phosphate attached to something that could be a good leaving group. And nature's pretty creative in how it does this. Step 8 is a simple, well, it looks simple on paper. The mechanism, it turns out to be somewhat complicated. The details are known, but it doesn't end up adding a lot to talk about them. So this one we're just going to memorize, if that's okay. Some of you will be okay with that. Others of you will hate it. And that's mostly how things go in my life. So I can tolerate that. All right, this is 3-phosphoglycerate. And the reaction that we're going to do next is a reversible reaction. It is catalyzed by an enzyme called phosphoglycerate. That's the name of the substrate, phosphoglycerate mutase. Now that's a new word. Mutase, what does that do? And you're probably thinking, it mutates stuff. No, but it sort of moves things around, which is probably the root word that's going on there with that name. Mutation involves change. Mutase involves a change in the location of the phosphate group. So you'll recognize this as an isomerization. You could ask me the question, why didn't they call it an isomerase? And I would say, I don't know. So the mutase enzyme moves the phosphate group over to the C2 hydroxyl instead of the C3 hydroxyl. It's still a phosphoester. That bond between the phosphate and the oxygen is still a phosphoester. And so this isn't really uphill in energy. And this reaction is again reversible. The delta G is essentially 0. But you'll see in the subsequent steps, getting that phosphate group attached to the C2 hydroxyl prepares us for something that is going to be good. So don't worry about the mechanism for this step. Your text points out that the mechanism goes through and, how do I spell there you go. Don't worry about the mechanism for this step. Your text points out that one intermediate along the way is phosphorylated at both the C2 and the C3 hydroxyl groups. How that happens, the details are known, but again, it's not really worth. I've talked about it before in previous sections of 352, and it didn't really add much, so we're just going to leave it out. If you want to know more, come talk to me. Okay, step 9, before we draw what the mechanism is, I'll write down what the name of the enzyme is. It's called Enolase. It's essentially, again, reversible. you start with this now 2-phosphoglycerate because the phosphate group is on the C2 hydroxyl. Based on the name enolase, what do you predict is going to happen in this reaction? It suggests something about making an enol kind of thing. Okay, good. I'll show you the product. The product now has a pi bond between C2 and C3. It still has the phosphate group on C2, but we're missing the C3 hydroxyl group. This is basically a dehydration reaction. Okay? What is the mechanism? It's probably E1CB. Probably a base removes from the enzyme, removes the proton from the alpha carbon to generate an enolate intermediate. I'm going to abbreviate the phosphate group like that. And then probably in a subsequent step, the negative charge on the alpha carbon kicks down to form a pi bond, and OH minus leaves as a leaving group to give you this product. And the product is called phosphoenol pyruvate. The name there doesn't make a whole lot of sense until you know what the structure of pyruvate is. Why would you know that? That's going to be the final endpoint of glycolysis. So this is pyruvate, and the enol of pyruvate would look like this. So this is pyruvate enol. These aren't intermediates in the reaction. These are just reference terms that I'm going to scoot down below so that you have an idea. We call this product phosphoenol pyruvate because it is the phosphoester of the pyruvate enol. Okay? So notice we still, in going from left to right, starting materials to products, we started with a phosphoester, and we're ending, again, still with a phosphoester. But you're seeing that the thing that the oxygen that the phosphate is attached to is not just an alcohol. Notice that if some nucleophile came in and attacked this phosphorus, this oxygen would leave not as a localized negative charge on the oxygen, but as a resonance stabilized enolate. So our strategy of getting the phosphate attached to something that was a better leaving group than just a regular old alcohol is what's guiding this process. Okay, questions about that step? Okay, ready for the last one. The neat thing about this final step is that it is irreversible. It is crazy downhill in energy. So we'll start with phosphoenol pyruvate. Okay, and then the enzyme that catalyzes this reaction is called, I'm going to get that wrong. Somehow it's not in my notes. I want to say pyruvate kinase. I think that's what it is. Yep. This is another enzyme that is named actually for the reverse reaction. This reaction will start with ADP. It will generate ATP. Again, this phosphate is going to become the gamma phosphate of ATP. The beta phosphate of ADP is going to act as a nucleophile to attack the phosphorus of phosphoenol pyruvate. I'm going to draw ATP here, or sorry, ADP here, and this is going to be the nucleophile. I'll draw just the first step. Lone pairs on the oxygen attack the phosphorus. We get our pentavalent phosphorus intermediate. And then actually, it might be helpful to draw, that intermediate so you can see what's going on and why it makes sense. So here is the pentavalent phosphorus intermediate. Here is the beta phosphate group of ADP. This is going to be the gamma phosphate group. I'm going to abbreviate the rest of this as AMP because there'd be another phosphate here, another ribose ring, and then the adenine. I hope that's okay with everybody. I just don't want to draw it all out. And then we're missing the carboxylate oxygen here. Electrons on one of the negatively charged oxygens will kick down and kick off the leaving group, and that generates ATP. And then here is the leaving group. That's the enolate. It could be protonated on the negatively charged oxygen to make the enol, and then would rapidly tautomerize to form the more stable keto form. What I'm going to do instead is just show electrons kicking down and the enolate getting protonated by the enzyme on the alpha carbon to give the ultimate product, which is pyruvate. Okay. This reaction is irreversible. It's downhill by quite a bit. I don't actually have the number written down, but it won't matter for our purposes. So again, in generating ATP, because we're making, and I'm not going to draw out the structure of ATP, but because we're making a phosphoanhydride bond in ATP, that's the bond between the gamma and the beta phosphate groups. What's over here, in order to explain that, what's over here has to have been a good leaving group. And if you think about why it's a good leaving group, there are two things to sort of ponder. The first is to look at all of those negative charges in this intermediate. Notice that you've got the pentavalent phosphorus that has 3 negative charges on it, and it's real close to the negative charge on the carboxylate. When the electrons kick down and the leaving group leaves, that charge repulsion goes away. So that's one of the things that helps pay for making that phosphoanhydride bond. The second thing that pays for it is that the leaving group is an enolate, and it is downhill to go from the enolate or even the enol to the more stable keto form. Just for fun, I mean, we've already drawn the pyruvate enol up here. This is the less stable form. So two things help pay for the pyruvate kinase reaction that makes ATP. Again, this is payoff. This happens twice for every molecule of glucose that starts in on the cycle. And the two things that pay for it is relief of charge repulsion, and the fact that the leaving group, which was an enol, tautomerizes to a more stable keto form. Okay, questions about that? Yes?
So like you mentioned earlier, the book shows it more like just one SN2
Uh-huh.
type reaction. Are we expected to know like the intermediate way for the test, or just the overall?
So I guess the question is, do I intend to write if I could put words in your mouth, if you'll forgive me. Do I intend to give you this as choice A and then as choice B exactly how it's shown in the text and make you choose between the two of them? No. Okay, others, yes?
Yeah, in step 7, between 18 is reversible.
Right.
What's the difference between that one and step 10?
What's the difference between step 7 and 10? I mean, two things. First, step 7 is the one that repays our ATP debt. The reason step 7 is reversible is because the bonds broken versus the bonds formed are similar in stability. You start with a mixed phosphoanhydride here in 3,1,3-bisphosphoglycerate. You make a new similar in stability phosphoanhydride in ATP. The reason it's irreversible for step 10, in some ways it seems counterintuitive because this is a phosphoester. That's the bond you're breaking. The bond you're forming is a phosphoanhydride. That should be uphill in energy. The things that pay for it and make it so downhill in energy are what we talked about, the relief of charge-charge repulsion and the enol to keto tautomerization. Okay, others? Yeah?
Where you have like the arrow pointing from like the not the pyruvate, but the pyruvate to the ATP. Wait, what was the like that kind of that arrow that kind of looks like it's going for ATP, but it's not. What is what's going on here?
Nothing special other than I wrote ATP is generated in this step. So I'm not sure. These are the two. These are the two products of that step. Yeah. Okay, others? Yes?
So for steps that are reversible, how does our body try to increase the yield or try to increase the...
So the question is, for steps that are reversible, how does your body deal with that and try to increase the yield? Reversible steps are fine as long as they're coupled to downhill steps that can pull things forward by Le Chatelier's principle. The 3 downhill steps are the 2 at the very beginning and the 1 at the end. And those steps are highly regulated. And that way, biology makes sure that if you commit that you don't commit a molecule of glucose to this process unless you really need it. Okay. Yes?
This might be a stupid question, but if there's like an overall net 0 output of ATP, how does it become efficient for like electron transmission?
So you said overall net 0 output of ATP? No, it's +2. So let's do the math. This would be a good review. We start at the beginning. We invest 1 molecule of ATP, so we're down 1. Second step, we invest another. Nope, that second step is isomerization to fructose. Third step is another ATP, so now we're down 2. Then in the 4th step, we split up into 2 pieces. And in the 5th step, we isomerize dihydroxyacetone phosphate into glyceraldehyde 3-phosphate. Thereafter, steps 6 through 10 happen twice because 1 glucose gives you 2 glyceraldehydes. So you are right that we've only shown in steps 6 through 10 making 2 molecules of ATP. We actually made 4. So we come out ahead. Okay, good. What else? All right, so that's 2 molecules of ATP for every molecule of glucose. That's good, but that's not really enough, or it's not all that could be done. And so nature has an additional metabolic pathway that's going to take you all the way from pyruvate, which is still a 3-carbon molecule here, to 3 molecules of CO2 and several equivalents of ATP. So we're going to learn about that as well. And that process happens in a couple of phases. The first involves conversion of pyruvate to acetyl-CoA. And then the second is the citric acid cycle, or the Krebs cycle, where we convert acetyl-CoA into CO2, and along the way make a lot of NADH and FADH2. Okay, so with that, we will forge along. So what we're going to learn about now is called, it's a 3-step series of reactions. But what we learn here will apply to another important molecule we'll see later on in the citric acid cycle. So it's pretty important to slow down and talk about it. This is the pyruvate dehydrogenase complex. So I need to introduce you to the key players, and then we'll deal with mechanism. Overall, in this reaction, you'll start with pyruvate. And we'll call this the pyruvate dehydrogenase complex, or PDC. That's a U there. My U's look a lot like V's. Pyruvate. When we're done, pyruvate will no longer be intact. One of the carbons is going to come off as CO2. The other two carbons are going to become acetyl-CoA. So we'll call this carbon 1, carbon 2, carbon 3. Carbon 1 ends up here, and carbons 2 and 3 end up there with acetyl-CoA. Of course, if we wanted this to work, we're going to need to bring in the coenzyme A thiol, which I'll show with that little arrow, and that becomes acetyl-CoA. Along the way, we're going to generate a molecule of NADH. So we're going to start with NAD plus in, and we're going to get a molecule of NADH out. So far this is looking pretty complicated. It involves perhaps more moving pieces than the other reactions that we've talked about so far. Unfortunately, we're not done yet. There's even more. So the other two cofactors are, one of them is called thiamine pyrophosphate. And the other is called lipoate. And both of these are important pieces. They're decently large cofactors, and I'm going to draw them now, though fortunately, like NAD plus and NADH, you don't need to know the whole structure. It's just a sub-part of the structure that's most important. So I'm drawing now for you thiamine pyrophosphate. It has this weird sort of almost pyrimidine type looking ring attached to one carbon, and then there's this second ring. It's the second ring that's the business end of the thiamine molecule. Sorry, that's not a nitrogen, that's a sulfur. There's a negative charge on this carbon, a positive charge on this sulfur, a methyl group here, and then two carbons here, and then a pyrophosphate group, which looks like this. And you've seen pyrophosphate before. You're going to see this again in biochemistry. I'm not going to ask you to memorize the structure, though you should be able to recognize it in a mechanism. The important part of the molecule is this ring here. So feel free to use R groups as needed when you're drawing mechanisms. The second, so that's one cofactor. The second cofactor is called lipoate, and this is a weird 5-membered ring containing 2 sulfurs with a stereocenter there, several carbons in a chain, a carbonyl, and then a nitrogen. And then it turns out this nitrogen is actually a lysine side chain. So this is the epsilon, delta, gamma, beta carbons of a particular lysine side chain in a protein that's involved in this process. So we'll just use, I'm just going to write a lysine side chain here, LYS, and we'll write a squiggly line there to say what it's connected to. So this is an amino acid in the enzyme that's been modified with something. It's this 1, 2, 3, 4, 5 carbon, used to be a carboxylic acid, which is attached to this 4-membered ring. And the key functional group here is this disulfide. So overall, that's what's needed to do this reaction. There's an important reactivity pattern that you should notice here. Overall, this reaction involves a decarboxylation because we lose CO2. Another thing to notice is that the reaction involves an oxidation. You can tell that's the case because we generated a molecule of NADH. Overall, we're going to put those two terms together. We're going to call this oxidative decarboxylation. And you've seen decarboxylations before, but never of this kind. Let me just remind you when you saw decarboxylations before. I tried to tell you in the earlier days of the class to always be on the lookout for beta keto acids because beta keto acids can undergo decarboxylation. The reason they undergo decarboxylation is that when the electrons kick down, you can leave the electrons from the bond between the carbonyl carbon and the alpha carbon on the alpha carbon, and that's a decent enough leaving group because of the influence of that carbonyl on the beta carbon. The resulting leaving group is resonance stabilized. That's not news to anybody. I think you remember that, or at least it's vaguely familiar. Probably should be more than vaguely familiar by the time you take the final exam, it's just as a warning. But you have seen sort of spontaneous decarboxylation of beta keto acids. The issue with this pyruvate dehydrogenase complex set of reactions is pyruvate is not a beta keto acid. Look at where the keto group is. It's on the alpha carbon. So pyruvate is an alpha keto acid, meaning if we had to just kicked down electrons and moved them here, they wouldn't be resonance stabilized. They'd just be sitting on that carbonyl carbon in an sp2 type orbital, just a totally unstable carbanion. So that gives you a sense for what we have to accomplish in this reaction. Somehow we have to make it okay for there to be a negative charge on carbon 2. And that's on the alpha carbon. And that's where these cofactors come in. We'll spend most of our time on the first step of this reaction because there are 3 things that happen in this pyruvate dehydrogenase complex. Okay. Questions about the overview? All right, let's dig in. So pyruvate is a ketone, or at least has a ketone in it, right? And ketones are pretty highly reactive. So you should not be surprised about the idea that a ketone should be an electrophile. What may be new and surprising to you is that the thiamine pyrophosphate, or if you want to call it TPP, is a nucleophile. Now I'm going to abbreviate it. I'm just going to draw the nitrogen and the sulfur parts. We'll put an R group on this positively charged nitrogen and another R group there on that carbon. Because you could imagine that the negatively charged carbon is nucleophilic. And indeed, that negatively charged carbon acts as a nucleophile, attacks the carbonyl carbon of pyruvate to give a tetrahedral intermediate. Now, if we wanted to, we could draw the negatively charged oxygen and then show what happens next in a subsequent step. What I'm going to do instead is just have electrons go up onto the oxygen whilst lone pairs on the oxygen pick up a proton, probably from the enzyme. You could do that in 2 steps. A lot of times when people are drawing biochemical mechanisms, they get sloppy with proton transfers in the way that I've shown. So here is the new intermediate. Here is the new bond in red, the new bond that we just made. Oops. Okay. These are carbons 1, 2, and 3 of pyruvate. We could label them as 1, 2, and 3. We could also label them as carbonyl carbon, alpha carbon. Maybe let's call that one beta now. Okay. Any questions about that intermediate? That's just standard attack of a nucleophile on a carbonyl. All right. Now, I told you that that thiamine pyrophosphate was kind of special in that it is a nucleophile. But interestingly, look at what it did for us. Now on the beta carbon, you have something that is not really a carbonyl, but it sort of looks like one. Can you see the resemblance between that and, if you relax your eyes a little bit, a beta keto acid? Yeah. The presence of that TPP group introduces something that looks like a beta keto acid. And the important thing is, if we did the decarboxylation and the bond between 1 and 2, the electrons in the bond between carbons 1 and 2 went out onto this alpha carbon, you would have a negative charge adjacent to a pi bond. That's a place where it could be resonance stabilized, right? So what we're going to do, and that'll maybe make more sense if we actually show it to you. Electrons are going to kick down to create CO2. We're going to break the bond between carbonyl carbon 1 and alpha carbon 2, and electrons are going to go onto alpha carbon 2. So here is the CO2 where carbon 1 is. That's the place at which we lose CO2. I'm going to draw what's left here. Sort of running out of space. That's carbon 2 and carbon 3. Lone pair is on carbon 2. And then over here, you've got the atoms from TPP. And do you see how, and I won't draw this resonance structure, but do you see how the negative charge is conjugated with this pi bond such that this lone pair could actually be on that nitrogen? Maybe let's just make the point more clearly by actually drawing the relevant resonance structure. I'm missing something, aren't I? Okay, so the use of TPP converts pyruvate into something that, if we do the decarboxylation, is now resonance stabilized. Okay? So that's the decarboxylation step. It's at this step, then, that we're going to use this resonance stabilized anion as an intermediate. And we'll use lipoate as an electrophile. This is actually basically an oxidation step. Lone pair electrons on the alpha carbon 2 are going to attack the disulfide. And I think it's sort of questionable which of the two it attacks. It may not matter. I'm going to draw what my notes show. My notes show attacking this one and then electrons going out onto the sulfur. That arrow should start with the negatively charged carbon, lone pairs on the negatively charged carbon to that first sulfur. Sulfur-sulfur bonds are relatively weak. So we've just made things worse, I realize. Gotten a little bit more complicated. I'm going to just put another R group here. For now, we can leave this sulfur negatively charged. It could pick up a proton from solvent. We won't really worry about it. Here is the new bond to carbon 2, blue carbon 2 that we just made. Here is the methyl group that's carbon 3. And then over here is still the TPP group. And that positive formal charge should be on the nitrogen. Okay? The reason you know that's an oxidation step is it resulted in an increase in the number of carbon heteroatom bonds. We didn't used to have a carbon-sulfur bond, now we do. Okay? In a lot of ways, this step is just like an enolate attacking some electrophile. It's like an enolate alkylation step. Okay, yes?
I wanted to help you out when you ran through the resonance structure. You got the rest of the positive.
Oh, thanks. Others? Yeah.
Do you have to worry about like steric hindrance at all with these interactions?
Steric hindrance, in what way? Like, were you thinking about which sulfur gets attacked, or?
Yeah, just like with like the size of the molecules, does that affect like reactivity at all with just between the two molecules?
Yeah, it's a good question, and you wouldn't really get a feel for how tough it is for these molecules to get close together unless you actually build space-filling models. I'm going to say part of what the enzyme does is it brings the two molecules together in the right orientation that they can make the new bonds without a huge amount of steric hindrance. Okay. Others? Right. So at this stage, then a base can remove the proton from the oxygen. Electrons can kick down, and then we can break this bond between TPP and carbon 2. And what will happen there is TPP gets regenerated. And what we're left with is a carbon 2, carbon 3 thioester. It's an unusual thioester because looks like I lost or gained another carbon. Whoops. It's an unusual thioester because it looks like this. but that's checked off. If you follow along what we wanted to start with, we started with pyruvate, and we wanted to lose CO2 and make a thioester. We don't have the coenzyme A thioester, but we did lose CO2, and now carbons 2 and 3 are at the thioester level. Okay? So that was step one. That's the first reaction to the pyruvate dehydrogenase complex. And that's the one we're gonna worry the most about. Other questions about that step? Okay, to connect loose ends, step 2 of the pyruvate dehydrogenase complex is going to take this thioester that we just made and it's going to do a transthioesterification reaction. So that's a lot of words, but basically we're going to swap out thiol groups. Coenzyme A thiol is going to do nucleophilic acyl substitution on blue carbonyl 2. And we're going to release the thiol. Okay, so this is just classic nucleophilic acyl substitution. To talk you through it, a base would remove this proton, the thiolate would attack the carbonyl carbon, you get a tetrahedral intermediate, the other thiol gets kicked off. That generates acetyl-CoA, and that is the substrate for the Krebs cycle, or the citric acid cycle. Step 3 is one that we won't worry about in a lot of detail. We won't draw this mechanism. It's a bit more complicated than we really need to worry about. But step 3 uses NAD plus to oxidize this dithiol up to the disulfide. Notice that what would have to happen here basically is, this isn't the way the mechanism works, but you can think of it this way. Negatively charged sulfur would need to attack this sulfur, and then H- would need to get delivered to NAD+. That should sound okay to you because you've seen NAD+ act before as a hydride acceptor. And so that regenerates the lipoate disulfide, and now we're ready to go for another starting molecule of pyruvate. Okay. This happens in mitochondria. Glycolysis happens in the cytosol. This process happens in mitochondria. And then what we'll talk about next, the citric acid cycle, also happens in mitochondria. All right. I think that's a decent enough place to pause. Wait, we got a question. Yeah.
Can you review step 2?
Review step 2. Deprotonate this coenzyme A thiol. Then attack the carbonyl carbon to get a tetrahedral intermediate, then kick off this other thiol as the leaving group. Okay, see you Wednesday.